I welcome all of you to this presentation on INFACT project. My name is Marko Komac. I'm representing one of the partners in the consortium, that's the European Federation of Geologists. And by coincidence, I'm also the president of the same organization. But as I said, I'm going to talk about a project that we are involved in, and I think it's going to be quite intrigued to all of you, quite interesting. And let's start. So INFACT project is a project funded by European Union through the Horizon 2020 research. And one part that I'm going to talk about today is addressing a novel and non-invasive exploration techniques and the way we see them as a sort of legacy of the project. So what is INFACT project in a nutshell? What does it represent? Basically, the goals are to the project looks into critical raw materials that European Union needs to address the issue of energy transition. And we base this project on 3 pillars. One is the supporting of development of non-invasive exploration techniques, which is the topic of this presentation. And then, of course, since this deals with exploration campaigns, and in Europe we have high density population, it also deals with the social perceptance of these techniques. So the second pillar is that the involvement of the stakeholders into the project. And since we don't want to invent the wheel, we just want to also look at the best practices all around the world and use them if they are usable in Europe. So there's 16 partners in the project, and they are listed on the right side of the screen. As I said, we're going to focus today on non-invasive exploration techniques that were tested or benchmarked within the project. So basically, objectives of the projects were 3. We could group them in 3 groups: to establish reference sites where the novel techniques could be benchmarked or tested, then to develop certification processes that give the official unbiased stamp whether a specific methodology is good or is it acceptable to this social part of this project. And the third one, we want to be as unbiased as possible when issuing these certifications, because then it gives it a higher credibility. So again, the focus of the project is going to be on the red text, so the technical performance of novel geophysical exploration techniques. In addition to that, since the European Union is paying for the project, they also need some sort of guidance. And what we want to do with the project is to set up a base to sustainable framework for mineral exploration and maybe also exploitation in the future. And for that, we are going to develop also some sort of roadmap that could be used by politicians and decision makers, where to go, in which direction they should go to follow this transition. So let's go now to the novel exploration techniques that are going to be the most of interest to you. What I'm going to present are some of the techniques that we've either benchmarked during the project at the reference sites, or we also try to upgrade them, develop and upgrade them through the project that lasted 3 years. I said lasted because it's almost at the end. There were several campaigns during the project timeline. First was already 2 years ago, then the second one last year. And this year we had some problems due to the COVID crisis. So some of them have been already performed. Some of them are still waiting to be performed until the end of the project, that is January next year. And just to give you an example of the techniques that we used, or the methodologies, methods of geophysical methods that we used in specific sites. This is one of the 3 reference sites. It's a Geier in Germany. I'm showing here different geophysical methods that we used to be benchmarked, to be tested against the real models. So this is, the benchmarking is not against something that is again modeled or non-certain, but it's always benchmarked again against the data from the drill holes and from in situ information. So let's see how these methods were actually deployed and what results showed us, or what were the outcomes. Of course, these are just some of the results, not all of them, because there are many. So let's see first the time domain electromagnetics. It studies the ground conductivity or resistivity of originated bodies in Earth. And this was further divided into two methodologies, 2 methods. Both were developed by Geotech, and these are versatile time domain electromagnetics. And those 2 are versatile time domain early times and versatile time domain max methods. And these are just some images from our field benchmarking. How does the system look like? Basically, it's mounted out on the helicopter, and the helicopter carries the transmitter and receiver at the same time, and then the data is collected. These are just technical representations. Those of you that are more familiar with them will find them interesting. Otherwise, we can just say that these are quite novel and rather advanced techniques. So from the first one, the early times versatile time electromagnetics, this is one of the results we got in Gaia, and it shows one section or one profile where we have the resistivity in colors, and then we have some benchmarking or comparison against the real data, and those are shown with different type of lines here in the graph. Then the second one that we've tested was versatile time domain electromagnetics, that's MAX. And these are again some specifications for those who are more interested in the technical part, in addition to just general description, which I'm currently giving. And there's another result, of course, again, as I said, benchmarked against the real information. And this one was done in San Antonio, that's Cobra de las Cruces in Spain. And the blue line represents the body, the ore body that was derived from the drilling information. So again, the data from the electromagnetics is compared with the real-time data, the real data, to see how good it performs. If you move further on to the next method that we used, this was the full tensor magnetic radiometer, and it was based on superconducting quantum interference device. And this was developed by Supracon, a German company. Again, it's mounted on the helicopter, and it produces and then also records or detects the backscatter information from the magnetic radiometer. This is a more detailed representation, and basically the sensor is defined in the 3-axis directions, so it can detect any difference, any change in magnetics in all 3 axes. And by that, we get the information of the change of the body, the border of the body, so we could actually get a rather good information on the size and the shape of the ore body. And these again are some results from the SQUID FTMG. On the left side, you have raw data. On the right side, you have already processed data in two directions, in X and Y directions. Further on, we used also audio frequency electromagnetics. And here we use Geotech Z-axis tipper and to get the right information from the method. There were also two orthogonal sensors put on the ground in two directions, in two axes, to measure the differences in electromagnetic frequencies. And this is one profile result. And I'm going to show you a much more detail on the next slide on those areas where we have large amplitude power noise, which are marked here by green rectangular. So if we look at one of the, as I said, one of the profiles to the areas where we have more suppressed results, the changes, and this could be related to geology, we can see that with depth it changes a little bit. And of course, this indicates that there are some ore deposits at specific depth that this methodology could detect. As we've flown with several detectors of electromagnetic radiations or waves, we also used additional detectors. One of them was radiometric detection, and here we measured with gamma ray spectrometer, and we measured the changes of uranium, thorium, and potassium at specific location. And we could see the results. We got some interesting results where these were, of course, again, benchmark again against the geological reality. So not a model, but reality. And here we have one of the results, uranium, showing the anomaly, which could not be linked to the geological model, but it's most probably related to the mining activities. While here, we could see that that disappears, and the presentation or the slide shows the potassium versus uranium and thorium radiation, and that was acquired again at Minas Rio de Tinto. When we look at the next methodology, which is airborne magnetics, here geometric cesium vapor magnetometer was used, and we could see on the right side where one of the results is shown, a really well-defined geophysical anomaly, but there's still no consensus between our interpreters, our experts on geophysical data interpretation, whether this is linked with geological source of or something else. While we look at the another result, here a rather easy interpretation was defined, and the anomaly is most probably linked with the infrastructure, so a human-induced intensity. In summary, if we look at the advances or advantages and shortcomings of the presented methods, we can easily say that novel geophysical non-invasive techniques enable us to detect deeper deposits than currently. They are also more advanced, and they could usually or often reveal unknown deposits until now, or better define suspected ore bodies that previously were not well known. Another advantage would be that these methods are rather fast, they could be widely used, and much easier to repeat than other ground-based methods. And of course, since it's always used as a sort of benchmarking, in a benchmarking process, We get critical assessment of their capabilities, whether these methods are actually useful or they need to be upgraded and developed in a different direction in the future. Of course, there are some shortcomings also. One is transportation, and I'm not talking here about northern issues, but these are rather sensitive equipment. So many problems can occur during the transportation. And also, since they are high tech, sometimes we do have customs issues with bringing them across the border. And most often they demand rather challenging or demanding data processing, and of course then the result derivation and interpretation. And with this, I finish my presentation. These are the contacts where you could easily get additional information if you contact either my colleagues or myself, or if you simply go to the webpage of our project. And I welcome you to do that. And thank you for your attention.